So in this question, we're asked to look for solutions to the equation a plus b times a minus b equals 45, where a and b are positive integers. So let's look at the factors of 45. So clearly, because a and b are integers, one of a plus b is going to have to be one of these factors, and the other is going to have to be a factor from the corresponding pair. And because a and b are positive, a minus b is going to have to be smaller than a plus b. So our possibilities are a minus b equals 1, and a plus b equals 45. A minus b equals 3, and a plus b equals 15. Or a minus b equals 5, and a plus b equals 9. Now at this point we have to be a little bit careful about making sure that these equations do give integer solutions for a and b, as opposed to, say, half integers. So we can solve these equations in turn. So let's just check that this does give us integer solutions for a and b. So if we solve this one, get that 2a equals 46. So this is going to give us that a is 23 and b is 22. We can similarly solve both other pairs of equations. So these do give us integers, and then we're asked to find all possible values of a. So this gives us the solution that a is 7, 9, or 23. And so we have 3 possible values of a, and the smallest is 7. So in this question now we have 2 sequences. The first of which I've written up on the board, so this is Priya's sequence. So it would be nice for us to be able to find an expression for the nth term of this sequence. So I'm going to write Pn for the nth term, with a convention that we start at 0. So 1,000 is the 0th term, and so on. And so I wonder if you could come up with a conjecture for what the nth term of this sequence is. Can you see any patterns? So one pattern that jumps out at me is that these numbers here, ignoring the thousands, are squares. And so that makes me wonder whether that pattern continues. So we're adding consecutive odd numbers with each step. And my question is this always going to give me squares? In other words, is this true? So there are a few ways you can see this. One nice argument is geometrically. So if I draw a square, you can see that over here, I have 1 dot. Here I've added 3 dots. Here I've added 5 dots. And at every stage, I'm going to add consecutive odd numbers of dots. And you can see that they're going to form a square. And so intuitively, this is why you can see that this equation is true. So if you see an induction, you might like to have a go at proving this formally for yourself, but I'm going to leave that as an exercise for you. So with this information, we can now say that Pn is 1,000 plus n squared. And we can treat Rhea's sequence similarly. So we're now interested in which numbers are in both sequences, i.e. which numbers are Pn for some n and also Rm for some m. So we're interested in solving the equation. A 1,000 plus n squared equals 3,025 plus m squared. Rearranging, and you might be able to spot that this is a difference of two squares, which means we can factorize as follows. So we want n plus m to be one factor of 2025, and n minus m to be the corresponding factor that goes with the first factor. Again, n and m are non-negative this time, rather than positive, as they were in the first part of the question. So this number has to be less than or equal to this number. So we're given in the paper that 2025 has 15 factors. So this corresponds to 7 pairs of distinct factors, and then we know that 45 goes with itself, because 2025 is 45 squared. So we have essentially 8 choices of n minus m and the corresponding pair of n plus m. And remember, in the first part of the question, we had to be a little bit careful about making sure that, given a solution for the pair n plus m, n minus m, that this corresponded to integers n and m. And really, all that matters here is that these two factors are the same parity, so that when we write n as n plus m plus n minus m over 2, as long as these are either both odd or both even, we're going to get an integer for n. And you can see that all the factors of 2025 are odd, so we don't have any issues there. So this means that we're going to get 8 different solutions, i.e. 8 different solution pairs n, m. So we're also asked to find the smallest number other than 3,025, which is in both sequences. So this is going to correspond to the smallest solution pair for n and m. So let's just write up what m is in terms of these two factors. So we can see from this that m is smaller if these two factors are closer together. So the case where m equals 0 corresponds to 3,025. So to solve this, we want to look for the pair of factors of 2025 which are closest together, but not the pair where they're equal. So not the pair where we have 45 here and 45 here. So after a routine check, we can see so we can now solve this for m and n. So we get, and we only really need to solve for one of m and n, so let's solve for n. We get that n is 27 plus 75 over 2. Which is 51. And if we substitute that back into the formula for Pn, we get that Pn is 3,601. And as we noted before, Because there are 8 possible pairs for n and m, this means that there are 8 distinct numbers which are in both sequences. And so this is the answer to the final part of the question.